Hi Prof, I'm Ting Ting from Team 6, and today my team and I will be presenting on our recommendations for World Health Organization regarding the implementation of relational or non-relational database. So however, in order to set a criteria, we definitely need to know what WHO needs, and that can be answered by understanding what WHO aims to achieve. So WHO or WHO is an agency of the United Nations with an overall goal to ensure that everyone on the planet is healthy. So as such, we established that the overall business objective of querying data is that they want to make sense of the data flooding in on a daily basis from various sources in order to draw useful insights in the global fight against COVID-19. So let's first move on to our relational database design. Based on the queries we need to answer, we know that we need to query by continent. Hence, to ensure that our queries are accurate based on the data we have, we know that our entity should contain continent information. However, this is lacking in 2 of the 3 tables. So as we can see from the right, we are given 3 unrelated entities, all of which have numerous attributes. For the purpose of answering our queries, we decided to do some initial data cleaning. First, we got rid of the rows that were not required for queries. So for example, in the mobility report, there were information pertaining to the sub-region of the country, as well as the overall statistic of the country itself. However, we assume that WHO is only interested in countrywide statistics since they operate on an international level, and thus decided to remove rows with sub-region 1, sub-region 2, and metro area field. So moving on, we also removed the columns that were not required for queries, as seen from the columns boxed in purple. So demographic data was not used at all during the queries. So last but not least, we also had to identify a common column to establish a relationship, and that was country. So this leads to our ER diagram made up of 4 tables, with the country table linking all 4 tables together. So we used an auto increment primary key, which created a unique identifier per row. So the reason why we didn't actually use composite primary keys based on the existing columns in the dataset was because it was mentioned that there might be a lack of data sometimes, requiring correction and maybe additional rows with date and country being the same. So this could lead to identical rows with primary keys being created. As such, with a unique identifier, the database can accept additional numbers to a certain country on a certain date with no problems to the database. Next, we inserted country ID as a foreign key for all 3 tables. This allows us to link and query across all 4 tables. We restricted on delete for the parent table as all 3 tables are linked to country and it is a strong entity. So by not allowing the most important table to be deleted, we can prevent any errors and ensure that data integrity is intact. We can then set the updates to the parent table to be cascading, such that should WHO choose to change the country ID, it will be updated on a timely basis and reflected in the rest of the tables. A little bit more about country table. It was created by taking all three tables and its distinct countries that we found, because some countries in the mobility report was not found in the OE data set. Hence, and for the response table, we appended the continent of Europe to all the tables and then did our research for the last remaining 4 countries which had continent missing. So this allows us to be able to query more data in the future if the need arises. So lastly, for relationships, a country record can have 0 to many records in mobility report, while mobility report record can only be traced to 1 and only 1 country. That is the same for other 2 tables. So after confirming that there were no transitive dependencies, we then concluded that our ER diagram has attained normal form and is now ready for queries. Hence, I'll pass my time on to Mr. ZHONG KANG, who will tell us more about the query execution.
Thank you, Ting Ting. Now I'll be moving on to talk about the relational database implementation. I'll go through the steps and thought process of my team's approach to resolve the SQL query. We'll be tackling on 3 main questions, which are 10, 11, and 13. So firstly, for question 10, we're supposed to generate unique country names that achieve more than 14 days of 0 new cases after recording more than 50 cases. Hence, for the output, we are only need to generate a list of country names that fits into the above condition. Now, looking at the code, we first select distinct country names from the table country, and we naturally join it to the test case count table, as each table has a common column which is country ID. Then we specify continent is not null to remove world and international, which are not continents. Then total cases more than 50 and new cases equals to 0 is the condition I mentioned earlier in the question. We use count country name more than 14, so that if a country name appears more than 14 times, it means it satisfies the condition where it does not have any new cases in 14 consecutive days. Hence, the output generated is 25 country for question 10. Next, moving on to question 11, we need to find the countries that have 0 new cases for 14 consecutive days, but suffered an increase of more than 50 cases in the next 7-day window. So this question is also similar to question 10, but it has an additional condition to it. So for question 11, we'll take a look at the sub-query first. The sub-query is similar to the question 10 query with total cases added, showing the total cases during the flattened curve period. Post 7 days is also added to find the end of the subsequent 7-day window. Then we will label this sub-query as A. Next, we natural join country and test case count as B, and inner join A to B such that A.post 7 days is equivalent to B.date, and adding a total case B to show the total cases at the end of the subsequent 7-day window. By doing so, we establish a link between both tables, showing the total cases before the 7-day window and after it. This allows us to find the difference between them for us to continue to the next step. So in the next step, we find the difference where it has more than 50 cases, and it refers to the upstick in new cases according to question 11. Outside of these two subqueries, at the start of the code, we select distinct country to achieve the final output for question 11, which is the unique location that has flattened the curve but suffered an upstick in new cases. Hence, the final output for question 11 is 2 countries only. And lastly, for question 13, we are supposed to conduct mobility trend analysis in Indonesia and identify the date when more than 20,000 cases were recorded in Indonesia. Based on the date, we must show the daily changes in mobility trends for the 3 place categories, which are retail and recreation, workplaces, and groceries and pharmacies. Based on the subquery, we are able to find out the date when Indonesia had more than 20,000 cases, as specified in the where condition. With the date, which is also referred to the D-date in the question itself, outside of the subquery, we have to filter Indonesia again to conduct the mobility trend analysis of Indonesia on that particular D-date. Hence, this will generate 94 rows of output. Now I'll be passing my time on to Yongjie to talk about the non-relational database.
Hello, I'll be demonstrating the implementation of non-relational database by tackling 3 questions from Appendix D with our NoSQL codes. First, we have question 10, where we are asked to generate a list of unique locations of countries that have successfully flattened the curve. The first part of the aggregation framework using the match operator, we match the world collection to the criteria, which is total cases having more than 50 and new cases being 0. As we are looking for the unique location of countries in this question, we also filter out documents where the location is from either the world or international by filtering out documents with no value for continent. Then we group them according to their location, followed by their total cases, and tabulate the total number of consecutive days by using the sum operator and the starting and ending date of the period by using the first and last operator, respectively. Lastly, we only match the documents which total number of consecutive days is greater than 14 to get the countries in the list that has achieved more than 14 days of 0 new cases. The next slide shows the list generated from the first part of the code. For documents that are grouped under a country with the same total cases, suggests that these documents are consecutive days with 0 new cases added, due to their total cases that remain the same throughout the period. Multiple occurrences of the same group location in the generated list, for example in this screenshot, we have Barbados and Brunei. They show the different periods of more than 14 days of 0 new cases within a country. Part 2 of the code groups the countries into a list of unique location that is also sorted alphabetically from A to Z. We separated the codes into 2 parts mainly because the first part can be outputted using the out operator into a temporary collection, output collection for the convenience of question 11. So for question 11, we are asked to generate a list of unique location or countries that have flattened the curve but suffer upticks in new cases. We have already generated a list from question 10. So for the first part of the code, we projected the temporary collection and added the ending date of the 7-day window to each of the period. And we output it into a new temporary collection called the new end date. The generated list from the temporary collection can be seen in the next slide. Next, we do an aggregation framework of the world collection, match the location to the ones found in our new end date, then we join the 2 collections together using a lookup operator with the date in the world collection equivalent to the date at the end of the 7-day window. This enables us to later project out number of total cases at the end of the 7-day window and the difference by subtracting it with the number of total cases from before the 7-day window. Then we match to find the differences that are more than 50 cases according to question 11. Finally, we output it into a temporary collection called countries to further sort out the distinct countries after that. The slide shows the output generated from the second part of the code, and the output of the third part shows the unique location, which is also the final answer to question 11. So these two locations are the final answer to question 11. Lastly, we'll look at question 13, which is the last question in Appendix D. We're asked to conduct a mobility trend analysis where we identify the date with more than 20,000 cases recorded in the country as a D-Day. Based on D-Day, we have to show the daily changes in mobility trends in the country for the 3 place categories. In our example, we'll be doing a mobility trend analysis on Indonesia, and the categories will be retail and recreation, workplaces, and grocery and pharmacy. So the first part of our query matches the world collection to documents having Indonesia as their location with total cases greater than 20,000. Then we group them according to their dates and sort them according to their dates as well in an ascending order. The results will show the dates from when Indonesia has more than 20,000 cases recorded, with the first result being the D-Day, which is the first day it broke to 20,000 cases. Then we output the result into a temporary collection, output collection. Then from the mobility collection, we match the country region to Indonesia and the date to be greater or equal to the first result of temporary collection, output collection by using the find one action, as the first result of output collection is the D-Day itself. We also make sure it filters out documents in the country region Indonesia with a designated sub-region because we are only looking for the changes in mobility trend for Indonesia as a whole and not specific to any sub-region in it. With how we match it, we also project the date and the 3 place categories to show the percentage change from baseline for each of the categories. Lastly, we sort them according to date in an ascending order. The aggregation framework will then generate an output that displays the daily changes in mobility trend in Indonesia for retail and recreation, workplaces, and grocery and pharmacy. This can be seen in the next slide where the D-Day is 22nd of May 2020. Now let me pass on to the next speaker.
Thank you, Yong. Now, I'll be moving on to talk about the recommendations that our team would like to propose to WHO. For this section, we'll be exploring 2 main ideas. Firstly, the incorporation of data visualization, where we believe that WHO can use data visualization to get a clearer picture of insights generated from the queries. Secondly, we'll be making comparisons between relational and non-relational database models to discuss which might be a better option for WHO. To start off, let us look at the incorporation of data visualization. We believe that WHO should not stop at just churning out data using the database models. Instead, they should proceed to using data visualization to generate insights from their query output, so as to come up with effective solutions. Taking the output from query 6 as an example, our team has made use of Tableau to transform the output into a graph. We've plotted the number of cases against different continents and has arrived at this figure as shown on the slides. From the graph, we can easily identify different trends such as Asia being the worst hit continent, North and South America having accelerating cases from the sharp rises, Africa and Europe having lower cases and slower rising of cases, and how in comparison to other continents, Oceania seems to be managing well, as seen from the low number of cases. Identifying such trends allows WHO to prioritize their resources in continents that require more attention, such as Asia, North America, and South America. Also, WHO can possibly look into how continents that are coping well with the pandemic are dealing with the situation, so as to generate possible solutions to help other continents that are not coping as well. From this, our team recognizes the effectiveness of using tools such as Power BI or Tableau to identify trend insights from the queries output of database models, and would hence like to propose to WHO the possibilities of incorporating data visualization into their process of data analytics. Next, we'll be moving on to look at the comparisons between relational and non-relational database models. A relational database such as MySQL stores and provides access to data points that are related to one another, establishing relationships between tables through primary and foreign keys. Future modifications can hence be made easily, since records are held in separate tables according to their categories. Also, Since access can be restricted to specific users only, relational databases seem to allow for better security as compared to non-relational database models. However, as our team looked into the advantages of using non-relational database models, such as NoSQL, we believe that using NoSQL is a better option for WHO as compared to MySQL. Now, Luis will continue with the reasons behind our options. Luis, please.
Thank you, Verene. Now I will be carrying on with the comparisons of relational and non-relational database models, as well as some key aspects that our team believe is crucial for WHO. While relational databases carry their own advantages as discussed above, it is crucial to note that relational database has its own limitations when dealing with large amounts of data. As compared to relational database models, non-relational database models have a higher scalability and is able to better deal with enormous amounts of data. This is particularly important for WHO since WHO is working with 194 member states and is definitely expected to deal with massive amounts of data. By using NoSQL, WHO can expect higher performance data processing as compared to using MySQL. Not only so, under instances such as the current COVID-19 pandemic, where the issue is expected to stay for a period of time, new data will be coming in continuously. Using NoSQL would allow new data to be easily updated into the collections as compared to MySQL where schemas would have to be adjusted. Additionally, during urgent periods where WHO might need data to be immediately processed, NoSQL has an edge as there is no need to design databases, unlike MySQL. We believe that all these advantages that come with NoSQL is particularly important for WHO, and since they are responsible for international public health and their actions will be able to impact many different countries globally. Faster data processing will increase their efficiency of coming up with better solutions to tackle different situations, thereby allowing serious issues to be dealt with at greater efficiency levels. Furthermore, when it comes to reliability, NoSQL provides a higher reliability as compared to MySQL. NoSQL supports auto data replication, where an additional copy of data will be stored on another server to carry out data analysis. The built-in failover function of NoSQL also allows for self-healing and reliable database clusters. While similar failover systems can be set up in MySQL, more resources will be needed to deploy and maintain a separate clustering layer, reducing the efficiency of identifying and recovering from underlying system failures. Since WHO has many different information coming from different states, data losses might cause troubles for them in terms of recollating data from all 194 member states. As such, the higher reliability of NoSQL is an important factor to take into consideration for an agency like WHO. From here, we conclude that NoSQL is a better option for WHO to handle the infodemic, where there is a large influx of data due to the higher efficiency and reliability involved. However, we recognize that different database models carry their own sets of advantages and disadvantages. While NoSQL might be a better option for WHO this time round, it might not always be the case. It is important for WHO to take a look at the nature of information that they are collecting, as well as the characteristics of their data when it comes to future data analysis, so as to employ a suitable database model. With that, we have come to the end of our presentation. Thank you.